Last we talked, we did this example LL parse, and we ended up with this stack progression, look ahead progression, and we numbered the steps. We went through the process of applying this to the LL parse table. Look familiar? Good, I'm not completely goldfish brained this morning. So not all grammars are LL1. We saw this earlier, but now we want to figure out a way to be able to parse a grammar that is not LL1, but is instead LLK for some constant K. So what this means is rather than just a single character look ahead like we had on the last slide, we need some way of looking ahead more than one character. We need to be able to store more than one look ahead character. There are some grammars that aren't LLK for any K. It doesn't matter how far ahead you look, you will still never be able to figure out which production to apply. And that's just one of the downsides of LL parsing. There exist some grammars that are not LLK. Usually at this point, we want to convert that grammar into something that is LLK, because you can have two equivalent grammars that have different Ks for the LLK. So here's something we should know. How do we identify that a grammar is not LL1?
Is there an easier way besides just starting the parsing and going until you find a spot where you can't find
What would that look like? How would we be able to identify it?
No one like a cell with more than one?
Yeah, if you have a cell in the LL table that has more than one production in it, that means that given the information we have, there are multiple possible productions that we can apply that have that particular target character or characters that we are looking for. So if we have a conflict in the LL1 table, then that tells us that it's not, the grammar itself is not LL1. So the conflict is that there's at least one entry in the table that has two or more right-hand sides of productions. So let's get an example of what that looks like. So here's a grammar. Go ahead and build the LL1 parse table for it. So the first thing you need to do is calculate first S and follow S. So start there. Do you remember how to calculate first and follow? So for first, this means that it's the set of terminals that can be the first one that is derived from this non-terminal being on the left-hand side. So if we have the non-terminal S, what is the set of possible terminals that could be the beginning of a string starting from that left-hand side? So if we apply this production, S arrow A capital SB, what is the first terminal or the set of first terminals that this could produce? Just A? That makes sense, right? There's an A right here. There's no way for this to be anything other than an A. If we apply S arrow AB, what is the set of all possible terminals that it could produce? Still just A. So regardless of which one we pick, we generate the terminal A. So first of S is just the set that contains A. Follow of S says everywhere that S appears on the right-hand side of a production, what is the next character that could appear? So we start by adding the end of string $sign to follow of S. That has to be in there. But then beyond that, we just care about wherever S appears, what is the set of terminals that can appear immediately after it? In this case, it's just B. So follow of S is just B and $sign.
Does it matter where you put the cash line in the?
No. It's a set, so order and multiplicity do not matter. So go ahead and now, given all of this information, construct the table. I chose something with a single non-terminal to make this table construction as easy as possible. But what does that table look like? So each row of the LL1 table is going to be a non-terminal, and each column is going to be a terminal union the $sign. And then for every production, S arrow something. Whatever starts that goes in the associated column. So we end up with a table that looks like this. It says that to get from the production S to a string that starts, or a substring that starts with the terminal A, you can apply any of the productions in that cell. So if we're at this non-terminal and we want a substring that starts with B, there's no way to do it. If we want one that starts with A, there are multiple ways to do it. If we see A as the lookup or the look ahead in the string, now we don't know which one of these productions to apply, which is why it is non-LL1. There's still ambiguity in which one we pick. And the goal with this look ahead is to remove that ambiguity completely. We need to have only one option for which production to pick in order to turn this non-deterministic algorithm that we generated last time into a deterministic algorithm that's going to allow us to decide the membership of some associated string that may or may not be in the language. So I talked about that in English. We can't decide between the productions S arrow A capital SB or S arrow AB with just a single look ahead character. What should we do about this? Any ideas of how we could move forward? Yeah.
Have 2 look ahead characters.
2 look ahead characters, what would that look like as a table? That's a great idea.
Each column would have 2 characters.
Yes, that's exactly what we're going to do. We're going to take every combination of 2 characters, and that's going to become a new column. Note that since $sign is also technically a terminal, we also need to include it as something that is possible. But also note that it can't be since it represents the end of the string, it can't be the first symbol in that. So you end up with a table that looks like this. So every possibility, AA, AB, BA, and BB, $sign can come second. So we have $A and B dollar. Or we have just dollar because nothing can follow the end of string marker. $A, for instance, wouldn't make sense. You can't have the end of the string and then some more string after the end of the string. As you build this up, you will see that with a look ahead of 2 characters, we can now distinguish between these 2 productions. The A capital SB, when we recurse the S, is going to generate another A first, regardless of which one we pick. So if we have the string, the substring AA as our look ahead, then we have to pick A capital SB to generate that first A so that we can generate the second A. On the other hand, if we have a 2-character look ahead and see AB, there's no way that A capital SB could generate that. Absolutely no way. The only way we can do it is to use AB. So with a look ahead of 2, we've removed that ambiguity, and we can now, with that much memory for 2 characters, we can decide between these 2 productions. Questions about LL1 versus LL2? So this grammar is LL2 because there's no ambiguity in the LL2 table. I will leave you now with this to work on in small groups. Here is a grammar, and the goal is to figure out what value of K is this LL for. You don't necessarily have to draw out every single table until there's no ambiguity. Use whatever logic you would like to try to figure this out. If that involves drawing out a table, great. If that involves some logic that doesn't involve the table, potentially great. Give you a couple of hints. Think about this on a variable by variable basis. How many look-aheads do we need for each non-terminal to figure out which production rule to apply, and then pick the maximum of those values? We'll start with the easiest one. What do we think the easiest one is here? There are two reasonable answers. We want to start with S, B, or C if we're trying to figure out the number of look-aheads that we need to determine which rule to apply. So that says that we have that non-terminal and we're trying to figure out, given a look-ahead of some length, which production to apply.
Yes.
I think S is the easiest one to go on. We have some ambiguity between A and A. So in the maximal case with S, I think that might be where this value of K ends up coming from. But I think that S is the hard one.
Perhaps C.
C might be fine. How many look-aheads do you think you need to figure out for C which production rule to apply?
2.
2? I agree with that. If we have just a look-ahead of 1, we see A and A, which looks the same, so we can't distinguish between the production rules. Where the look-ahead of 2, we either see AB or we see $, the end of string marker. So that is enough to distinguish between the productions of C. So the C production by itself is LL of 2. What about B? Just need 1. We'll look at 1. This production, if you see a B, sorry, A, this production, if you see a B. Great. Now the harder one. How many characters do we need to distinguish S? How do you get 5?
Because you can have 3 A's and then B, whether you use the first one or the second one.
Yeah, so the idea would be to start using these productions and see how far you can get and produce exactly the same string. So if we start with S arrow A capital B, how are we going to resolve this capital B? Because we need to produce a second A, right? So we don't want to apply the second one. We want this to map to this. So we're going to choose to make this B into AB. So we end up with A capital B. Maybe we can start doing this in parallel. So we have S arrow A capital C. So we can see that between these, now we've generated the first 2 characters the same. So what can we do in order to continue this process of trying to generate the same string that started with these 2 different productions? What do we want to apply?
Apply C. The second one.
C to AB capital C?
Yeah, these.
AB capital C. And then here, what rule do we want to apply?
AB.
B to AB. Yeah, we generated the first 3 characters the same. Now we want to apply a B here, so this tells us to apply this production to this B. And then this C can become an A. How many look aheads do we need to distinguish these two strings from each other? 5. The difference is on the fifth one. If we just look ahead 4, they look identical. So this is the non-table logic that you would go through in order to figure this out. If you were doing this algorithmically, maybe you would generate the LL1 parse table. You would see some ambiguity. You would generate the LL2 parse table. You would see some ambiguity. You would generate the LL3 parse table. You would see some ambiguity. You would generate the LL4 parse table. You would see some ambiguity. You would generate the LL5 table. And finally, there would be no more ambiguity. And you could terminate saying that this grammar is LL5. That sounds painful. Remembering an eraser, the bane of my existence. All right, so this is all the work we just did. Between all of these rules, C, B, and S, the greatest was 5. We needed 5 characters to distinguish between them. So because of this, the grammar is LL5. Questions on this intuitive work? It's not really algorithmic necessarily, but it's a way of problem solving it if you see it yourself and you want to know the LL value of a grammar without algorithmically generating all the tables. All right. Last one. Feel free to talk about this in groups. Everyone seems to want really small groups today. Yeah,
Is this one of the ones where we can't know for sure?
that is correct. This is not LLK or any K. What makes you say that?
If A will only ever produce just a bunch of A's, then you don't know which one to apply.
Yeah, exactly. Let's say you have a billion A's in a row that eventually terminates. Did that start by using the first production or the second production? In A arrow, one of these two. Who knows? Could be either of them. Given that string, there's no amount of look ahead that would ever tell you that. This will always be ambiguous. You will always have the option between picking one or the other. But there's no way for us to know that in general. With the example of a billion A's, it wouldn't matter which ones you picked, as long as you could eventually terminate. But maybe there's one correct one and one wrong one. And there's no way to know. So again, for A, first two productions can generate an arbitrary number of A's. That shouldn't say infinite, should say arbitrary. And no value of K will be able to distinguish them. So the conclusion is that the grammar is not LLK for any K. Questions on LL parse tables? LL grammars? Non-LL grammars? This is the last thing in the LL set of slides. So this should be all the information you need to be able to complete the homework. It's the last thing that's going to be on the study guide. So everything we do from here on out is going to be interesting material that will not be tested. Which is probably good because LR parsing is harder. All right, LL seems not too bad, right? So why do we even bother with LR parsing? The very last thing we looked at was a grammar that wasn't LLK for any K. When you have a grammar that is not LLK for any K, we can't run the LL algorithm on it. It's just not going to return us an answer. And maybe there exists an equivalent grammar that is LLK for some K. But what options do we have? We would still like to be able to use that grammar for parsing. The downside is that LR grammars are more complicated than LL grammars. The upside is more grammars are LR of K for some K than LL of K for some K. So if you implement LR parsing, you're going to end up with a wider, the word I'm looking for, compatibility, I guess, with more grammars. So just like we started before with LL parsing, we're going to look at how we could construct an NPDA from a context-free grammar that models the LR parsing process. So we know that there are multiple separate NPDAs that are equivalent that model the same language. So we're going to now show for the same grammar a way to construct a different NPDA that is equivalent, also recognizes the language, and will allow us to move forward. So same three states as before, Q0, Q1, and Q2. We are used to Q1 being the state that has all of the work being done in it. In an LR parsing NPDA, Q0 has all of the work being done in it. So Q0, state with the most transitions. We need to add all of the following productions to Q0. So in our context-free grammar, we have some non-terminal arrows, some sequence. We're going to call this X sub 1, X sub 2, up to X sub n, where each X sub k is either a terminal or a non-terminal. So it's just breaking down the right-hand side into its individual symbols. For each one of those, we want to add a transition rule. The transition rule is that we are going to say, from state Q0, we are going to pop all of the right-hand side and replace it with the left-hand side. Now, this models bottom-up parsing the way that we talked about before, because we were doing lots of replacements. We started with the string and we started finding sections of the string that mapped to right-hand sides, and we replaced those with the left-hand sides and eventually tried to derive the start non-terminal. That's how we looked at and did bottom-up parsing before. So that's exactly what we're going to model here. If there's a particular sequence that we see that maps to a right-hand side, we can replace it with a left-hand side. So we just need to add to the NPDA all rules that do that. We're gonna give a name to this kind of transition. We're gonna call it a reduction. Because we're taking lots of symbols, our right-hand side, and we're replacing it with a single non-terminal, its left-hand side. So a reduction in the length of the string. We need one more kind of transition rule here. For every terminal, we need the ability to read that terminal from the string. Or if we see it on top of the stack, and it happens to be the next character in the string, we can both pop the terminal off the stack and move forward in the string. So we're going to basically do exactly this. So we're gonna go from state Q0 to state Q0. We're going to pop the terminal, and we are going to push the terminal and the stack symbol concatenated, which is a kind of really strange way of doing this. We're gonna call this a shift. Finally, we need two more transitions to finish everything off, and this is going to get us to state Q1 followed by Q2. To move from Q0 to Q1, we need the very top of the stack to be S, the start non-terminal. That says that we were able to derive the start non-terminal out of the string. So there's the associated transition. We make no change in the string. We pop the S off the stack, and we move to state Q1. The last thing we can do is move from state Q1 to Q2, and to do this, the stack has to be empty. This prevents us from something like having a case where maybe we have a production that says S arrow lowercase a, capital S. We could derive the capital S on top of the stack, and then there would be two more A's underneath it. So we would pop off the S, but the stack wouldn't be empty. So we can't have Q1 being our final state for that reason. There could still be stuff left on the stack that tells us that we produced an S, but not the S that represents the entire string, an S that represents a substring of the string, which is still not acceptance. We need to be able to generate the entire string, which means that what needs to be left on at the end is just a capital S. That can be the only thing left on the stack at the end. If that's the case, we can move on to state Q2, the final state with an empty stack, we accept. So let's take a look at what this looks like. So here's a grammar, and we want to make an equivalent NPDA that models the process. So just as before, we're going to make our initial three states. We need to add the reduction transition rules. So for each transition here, we need to, once we identify the right-hand side, add a transition that allows us to pop the right-hand side and push the left-hand side. We're now going to allow us to concatenate lots of things together and try to remove them all at the same time. This isn't technically allowed, so we will eventually show how we deal with this in the actual LR parsing process. But for now, it's a shorthand in the NPDA that allows us to do this. We need the shift transition rules. So for every possible terminal X, we are going to say, all right, we can go from state Q0 to state Q0. We pop an A and add an X for that. We add and end up adding the AX, the concatenated version of that for all terminals X. Sorry, terminal or non-terminal or the bottom stack character. X can be any of those three possibilities. So we end up with the ability to take an A and get AA, AB, A capital S, something of the sort. These are the shifts. The final transition rules, we allow going to state Q1 on a capital S and state Q2 on an empty stack. So the entire NPDA ends up looking something like this. There are way more transitions than this because this has to be for all possible X, but we just shorthand it so it's actually visible. We will see much better, I think, what a shift looks like as we go through the process that we went through with the LL parsing. But for now, are there any questions on this logic or how you produce this NPDA or how it models bottom-up parsing? All right, so how do we have a string? We have this NPDA. How do we actually parse the strings? So shifting is what puts the character that we see from the string onto the stack. That's what we mean by a shift. We're going to move the input characters beyond, and that's going to move it onto the stack. Because we can't look at the entire string at once, we can only look at what's currently on the stack. So we're going to start shifting symbols from the string onto the stack. And non-deterministically, we're going to, when we can apply a rule, pop some right-hand side of a production off the stack and replace it with the associated left-hand side. So we're going to apply one of the reduction rules. So you continue to shift characters from the string onto the stack until somehow you can map a right-hand side to a left-hand side. Non-deterministically, you're going to fork your program at that point, continue shifting in one of those forks, and do a reduction in the other fork. I mean, just whenever you can do that, you'll fork your program, and non-deterministically, as long as one thread ends up with S and only S on the stack, do you go through this process and accept? That means that there is a way via some sequence of productions to get the string from the start symbol, or more like what this is doing, taking the string and replacing it with left-hand sides until eventually we just have the start non-term. So these steps are non-deterministic. Choosing shift to reduce happens in parallel. At least that's how I like to think of non-determinism in this sense, is we're just doing them in parallel. Just as before, we need some additional information to turn this non-deterministic process into a deterministic process. So how can we do that? We can store a look ahead just like we did with LL parsing. But with LL parsing, we just cared about the next character in the look ahead or the next substring in the look ahead. With LR parsing, we actually need to keep track of the entire rest of the string. Let's take a look at an example. So same grammar as before, same string as before. So we're doing the exact same work that we did on the LL slides, except now we're going to do it in an LR bottom-up fashion. So here's what it looks like. We have our states, and our states are just going to stay Q0, 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 Q0 until we're at a position where we can accept. The operation that we have here tells us whether it's a shift or a reduce. So we also keep track of the look ahead for each step. So we look at the rest of the string. So right now, when we begin, there is no ability to reduce. So we don't even need to consider reducing. So we just shift the first character onto the stack. So we shift the A onto the stack. We get this AZ that was the concatenation from before. And that becomes the first thing we do. We continue to shift and move our look ahead, shift, move our look ahead, to the rest of the string, until now we can actually apply a reduce. We can take this terminal C and we can apply this production in reverse. So we replace the C with the capital A, which is what we do there, and that's our first actual reduce operation. We then shift another character on, and then eventually we see, oh, look, the top of the stack is the right-hand side of a particular production. So we can replace this A capital A B with the A capital A B going from right to left here. So we can do a reduce there into capital A. And now we have this A that can become capital S. So we reduce again. Then we do our final shift, putting the B on, and then this A capital SB maps to that A capital SB, so we can do one last reduce, getting just the S on the stack. We then transition from Q0 to Q1, transition from Q1 to Q2, and accept. The look ahead can end up being the end of string character, the $ from before as well. So we need to store just a little bit more information as we do this. But there's still some non-determinism here. In step 5, we could have done either. We decided to shift. In step 7, we decided to reduce. There were multiple options in each of those places. How did we know to shift or reduce there? That's what LR parsing is going to be able to do for us. Right now, we're just modeling, stepping through the NPDA. And as we do that, we're going to end up having to make decisions. If we were truly mapping this process, we would need to fork this process at each one of those locations and figure out what happens if we shift, what happens if we reduce. That ends up being an exponential algorithm to do deterministically, so we need something more intelligent to do to be able to take this exponential complexity, because in the worst case, you could be choosing shift or reduce at every single step, which would fork your program 2 to the number of operations times. And that would be really bad. So we need something to help us turn this into something that's deterministic and efficient. So we can guess by looking at the look ahead and the stack contents, but it's really difficult to algorithmically produce that. As humans, we can look ahead and make an intelligent decision, but a machine would not be able to do so without fully iterating through everything. Once we know LR, we'll be able to eliminate guessing completely. How are we going to do that? We need to define 2 new terms, an item and a closure. So the first is, we would like to be able to know when a production's right-hand side is on top of the stack. We know we can't dig down the stack. The stack is a stack of plates that you can't see from the side, you can only see from the top down. So there's no way to know what's currently on the stack. We need some way of storing that information separate from what's in the stack. So each symbol is put on the stack one at a time. To figure out what's on the stack and what's not mapped to a production, we need some way of adding some kind of storage to the right-hand side of every production to say how much of this production is currently on the stack. So we're going to use the dot symbol for this. We call this an item. It's a production with kind of a placeholder in it. So if we just write out the production, we put a dot somewhere in that production that indicates that everything to the left of that is on top of the stack, and everything to the right of it is not. That tells us if we were to continue to shift and add the associated things to the right, or reduce and be able to get to that point, then we would know whether or not what's on top of the stack is the right-hand side of a production. Does that make sense? You're just kind of putting a storage marker in it. Note that this can appear anywhere in the production. At the very beginning, that tells us that there is absolutely nothing on the stack that relates to this right-hand side. At the very end, that tells us that we have the ability to reduce right now. Everything that's on top of the stack maps directly to the right-hand side of some production. And because of that, we could choose to reduce if we wanted to using that production. So that's what's going to tell us when we have that ambiguity of a shift or a reduce. Is if we have the marker on the very right-hand side of a production. So if we have n symbols on the right-hand side, there are n+1 possible positions for the marker. Questions about the marking process? So if we had the S arrow A, S, B, we could have S arrow dot A, S, B, S arrow A dot S, B, S arrow A, S dot B, or S arrow A, S, B dot. 3 symbols here, 4 possibilities for this production for where the marker could be. This tells us that there's nothing on the stack that is relevant to this production. This tells us that everything on the stack is these exact 3 characters on the top of the stack. So we could choose to replace the top 3 characters of the stack with S if we wanted to. This goes without saying. Basically, if the marker is directly to the left of some non-terminal that is in the right-hand side, then that non-terminal is not currently on the stack. There may be some additional things that could be reduced to that, which is why we need the concept of closure. In order to move the marker right past a non-terminal, we have to eventually reduce to get that non-terminal. Since we start with just a bunch of shifts, until we do a reduce, there are no non-terminals in the stack anywhere. Right? If our string was ABC, AB, if we just did a bunch of shifts, we would shift A, B, C, A, B onto the stack. There are no non-terminals, so we have to do a reduce. So if the marker on some production is right before a non-terminal, in order to be able to move past this non-terminal, we eventually have to reduce something to get that non-terminal so that we can move this past that. So the reason to do a reduction or a reduce operation is to get to the point where we can move this past. At least as an option, something we can do. So to do this, we need to define a closure. So a closure is a set of items. We're going to initialize the set of items to contain just a single element. And these elements are going to be productions with dots in them. So the closure of some substring W dot some substring V, we're going to have a single element in there, the non-terminal that maps to that with the associated thing. We're then going to try looping through this process, adding items to the set until we go through a step where we do not add anything. For every production in the set, so we're going to start with just that one, we're going to figure out if the dot appears before a non-terminal. We're just going to call this B for the sake of argument. So we're going to add a new production to the set B arrow dot the right-hand side for every possible right-hand side where you have B arrow something. We'll get you an example of this. And actually, I don't know if we're gonna have time for that example because we're basically out of time. So we will come back tomorrow and start here. Redefining closure and then looking at an example that will hopefully help make this make more sense. Right, I will see you all tomorrow.